Hello, this is our group assignment for KIG1004, Group 1, Semester 2, 2018 and 2019. Material application. The material that we chose is copper wire in electrical appliances. Below are our group name member. Introduction. Copper wire in electrical appliances. The major use of pure unalloyed copper are based on its high electrical and thermal conductivity, as well as good corrosion resistance. Almost all alloying elements are detrimental and to the electrical conductivity of copper, making the purity of the metal an important issue. Commercially, or is represented by UNS member C100, C100 to C13000. The various grade of unalloyed copper differs in an amount of impurities and therefore do behave differently. Oxygen-free coppers are used in appliances or application requiring high conductivity and exceptional ductility. Microstructure of copper wire. The microstructure of hot-rolled copper contains many small grains. Parallel straight line extending across many of the grain are called annealing twins. The interdendritic network of copper oxide particle was destroyed by hot rolling. They appear after a metal has been mechanically worked at a high temperature, called annealing, and deform. After hot rolling, copper oxide particles change form and are represented as stringers or a line row of dark particles. The oxide particles are much larger and few in number than in the case of microstructure. This figure shown is the microstructure of copper wire. Next is the cross section of copper wire. As you can see, this is an insulated copper wire coated with very thin layer of insulation, such as rubber or polymer. It is used in construction of transformers, inductors, motors, speakers, hard disks, heat actuators, electromagnets, and other applications that require tight coils of insulated wire. The second figure is cross-section of copper wire that is uncoated. So, copper wire in electrical appliances. A copper wire is a single electrical conductor made of copper. Can be insulated or uninsulated, as we can see in the figure. Copper cable is a group of two or more copper wire bundled together in a single sheet or jacket. Basically, it's used in power generation, power transmission, power distribution, telecommunication, electronic circuitry, and countless types of electrical equipment. It has been useful ever since telegraph and electromagnet were invented. Copper is the most widely used conductor in many kinds of electrical wiring. It has the lowest resistance to flow the electricity of all non-precious metal. Electrical writing in building is the most important market for the copper industry. So copper undergo drawing process to make a wire. Drawing is a metalworking process consisting of reducing cross-section by the wire through series of dies. Copper becomes harder and brittle due to the drawing and is not suitable for making it as a wire because it's too stiff. Grain refinement is one of the most effective way to improve the strength of the material without losing on ductility. ECAP, HPT, MAF, and ARB are grain refinement method based on severe plastic deformation. Annealing is a heat treatment process that alters the physical and sometimes chemical properties of a material to increase its ductility and reduce its hardness. So, as we can see in the figure above, annealing affects the size of grain. Annealed copper has lower grain size because annealing treatment causes severe recrystallization, where new strain, free grain, nucleate, and grow to replace the former grain. This restores the ductility of cold work copper, so it can be cold worked further without breaking.
There are a few relationships between the microstructure with the copper wire's property. The first one is the development of the fiber texture in the drawing, accompanied by an increase in the hardness with the deformation. So depending on whether the level of deformation increases, the drawn wire acquires a texture fibrous microstructure. This texture is frequently observed in the wire drawing and is known as the texture of fiber or fibrous texture because it resembles the arrangement of a fibrous material. A structural scale is merely for an orientation in the direction parallel to well-defined crystallographic axis of the wire. This texture is symmetrical about the axis of the wire, known as the fiber axis. Micro-hardness measurements shows an increase in the hardness of the drawn wires with the deformation level. These increases is very strong in the first stage of the deformation and tends to stabilize later. This type of result has already been met on the steel wire drawing. This hardening is interpreted by the hardening mechanism, leading to a very high dislocation density in the deformed material. The second relationship is the annealing process, which has something to do with the heating and the cooling process of a materials that leads to the recrystallization of that material. In an experiment conducted, the mechanism of the recrystallization process is triggered just after the first minute hold when it is heated up till 260 degrees Celsius. The latter structures develop over the extended holding time. This result is consistent with various studies and theories of recrystallization, as a large plastic deformation leads to a large energy stored in the drawn wires by means of a large number of dislocations, which causes the onset of recrystallization mechanism. In the graph shown, the curves of micro-hardness shows a softening for all drawn wires and annealed at 260 degrees Celsius. This decrease is larger for the weakly deformed wire. Another relationship that we can deduce from the relationship of the microstructure and the copper wire is the tensile test and the measurement of the electrical resistivity. The resistivity measurements and tensile tests were made at the physics lab of ENICAB company in Nigeria for the drawn wires and then after annealing at 260 degrees Celsius. The results of the tensile test before and after annealing presented in the table shown in the slide. The results of the resistivity before and after annealing at 200 degrees Celsius are illustrated in figure 5. We note a clear increase in resistivity with the reduction rate by drawing. On the other hand, annealing at 260 degrees Celsius for 30 minutes, maintaining caused a slight decrease in resistivity by porting the state drawn. This result is in conformity with the results of the effect of deformation on electrical conductivity of copper and those deformed copper. The calculation of resistivity evolution exhibits an increase in resistivity of 1.7% between the 28.59% and 84.59% of reduction level. Related to the previous studies, it was found that the deformation of copper contains a high density of dislocations and also a small vacancy of clusters formed by the agglomeration of deformation-induced vacancies. The presence of these defects is barriers against the movement of electrons in the metal.